July 18, 1942. The skies over Germany are a canvas of smoke and fire. The roar of piston engines fills the air, but today, something different cuts through the chaos. A sleek, unfamiliar silhouette streaks across the sky, the Messerschmitt Me 262. The world's first operational jet fighter powered by the revolutionary Jumo 004 turbojet engine. In the midst of the Allied bombing campaign, the Germans unveil their secret weapon. The Me 262 is a marvel of engineering, its twin engines propelling it to speeds previously thought unattainable. But beneath its advanced design lies a series of challenges that will soon become apparent. As the war intensifies, the Allies begin to take notice. The Me 262's potential is undeniable, but so are its limitations. The Jumo 004 engine, while groundbreaking, is plagued by issues that hinder its effectiveness in combat. The arrival of the Me 262 marks a new chapter in aviation history, one that will see both triumph and tragedy. The Stormbird has taken flight, but its journey is far from straightforward. May 1945. The war in Europe is nearing its end, but the skies still echo with the roar of combat. In the twilight of the Third Reich, the Allies are closing in on the remnants of the Luftwaffe. In the forests of Bavaria, a small group of American soldiers moves cautiously through the underbrush. Their mission is clear: locate and secure any remaining German aircraft for intelligence purposes. Among the wreckage of a Luftwaffe airfield, they find the Messerschmitt Me 262, the world's first operational jet fighter. The aircraft is a testament to German engineering. Its sleek design and twin engines a stark contrast to the propeller-driven fighters the Allies are accustomed to. But it is more than just a trophy. It is a key to understanding the future of aerial warfare. The Americans waste no time. Under the cover of Operation Lusty, a covert initiative to exploit German scientific and technological advancements, the Me 262 is carefully disassembled and transported to Wright Field in Dayton, Ohio. Here, it will be subjected to rigorous testing by the United States Army Air Forces, USAAF, engineers. As the aircraft is unloaded, the engineers gather around, their faces a mixture of awe and skepticism. They know this is no ordinary aircraft. This is a glimpse into the future of aviation. The Me 262 is carefully inspected. Its engines, two Junkers Jumo 004 turbojets, are removed and placed on test stands. The engineers are eager to understand the mechanics of this revolutionary design, to learn from its innovations and, perhaps, its shortcomings. The first test runs are conducted with bated breath. The engines roar to life, their thrust propelling the aircraft forward with unprecedented speed. The engineers take meticulous notes, observing the performance, the vibrations, the heat signatures. They are witnessing the birth of a new era in aviation. But as the tests progress, the engineers begin to notice troubling signs. The engines, while powerful, exhibit signs of rapid wear. The turbine blades show signs of softening and the compressor fans are prone to failure. The engineers realize that the materials used in the construction of the engine's magnesium alloys and other lightweight metals are insufficient to withstand the extreme temperatures and stresses of high-speed flight. The engineers confer with one another, their faces etched with concern. They understand the implications. While the Jumo 004 is a marvel of engineering, it is not without its flaws. The rapid wear and limited service life of the engines pose significant challenges to its operational effectiveness. Despite these challenges, the engineers are undeterred. They continue their tests, pushing the Me 262 to its limits, seeking to understand its capabilities and limitations. They know that the knowledge gained from these tests will shape the future of aviation, influencing the design and development of jet engines for years to come. As the sun sets over Wright Field, the engineers gather one last time to review their findings. The Me 262, with its revolutionary design and powerful engines, has provided invaluable insights into the future of flight. But it has also highlighted the challenges that lie ahead, the need for more durable materials, more reliable engines, and more advanced technologies. The hunt for the Stormbird has yielded its secrets. The engineers have learned much, but they know the journey is far from over. The future of aviation is unfolding before them, and they are determined to be a part of it. May 1945. Inside the cavernous hangars of Wright Field, a smell of oil, hot metal, and burned insulation hangs heavy in the air. The ceiling beams groan under the weight of equipment, and the hum of fluorescent lights buzzes overhead. Engineers, technicians, and a few curious pilots move carefully around the Me 262, now stripped of its camouflage and markings. Each step echoes against the concrete, a reminder that this is hallowed ground for technological discovery. Captain John Jack Reynolds, A young USAAF engineer with a knack for mechanical intuition leans over one of the Jumo 004 engines. His fingers trace the turbine blades, slick with oil. "These are fragile," he mutters. "You wouldn't last a dozen hours at full throttle." Around him, his colleagues nod grimly, scribbling notes and diagrams. They are confronting a paradox: a jet engine that can propel an aircraft faster than anything they've flown, yet crumbles under its own heat. The first test is scheduled for early evening. The engineers wheel the Jumo 004 into the test cell, a concrete wall chamber equipped with heavy ventilation and instrumentation to monitor temperature, RPM, and thrust. Outside, the wind carries the distant clatter of the airfield. Inside, the chamber is eerily quiet, save for the occasional clink of tools and the murmur of technicians double-checking connections. Lieutenant Harold Banks, responsible for instrumentation, calls out figures from his clipboard. The engineers ignite the starter motor and a soft whine begins, slowly building into a roar. The engine vibrates violently, the floor plates shuddering beneath its thrust. Sparks flicker briefly from the ignition port, and the smell of burning magnesium fills the air. Sweat beads on foreheads and some step back instinctively. "Steady," Reynolds whispers. His voice carries both awe and fear. The readings climb, RPMs rise toward operational levels. The jet's power is undeniable. Compared to piston engines, the acceleration is instantaneous. The test cell fills with a sound unlike anything the engineers have ever heard: a screaming, metallic howl that seems to pierce through the walls. And then the warning signs appear. Small cracks form along the edges of the turbine casing. Thermal stress causes the blades to warp slightly. Reynolds points to the compressor fans, where discoloration hints at overheating. "This won't last," he says quietly. "Maybe a few flights before it fails." The engineers debate what they are seeing. They are aware that German industry was constrained by wartime shortages. High-grade alloys were reserved for projects like the Me 262, but even then, corners were cut. The Jumo 004 is a product of genius constrained by necessity. Its brilliance is visible, but so is its fragility. Each failure during testing is meticulously recorded. They observe fatigue cracks, bearing failures, and even complete turbine seizure in repeated runs. Yet for all its flaws, there is something hypnotic about the engine. Reynolds watches the exhaust flames ripple from the rear nozzle. "Imagine flying this. The speed, the climb rate," he murmurs. Other engineers nod, acknowledging the transformative potential of jet propulsion. They know that the lessons learned here will accelerate American jet programs, like the P-80 Shooting Star, which is still under development. During breaks, the team exchanges observations. Some speak of the challenges of maintenance, others of metallurgy innovations needed to endure such temperatures. They discuss alternatives: coatings, cooling passages, and better alloys. They study every detail, from oil pumps to blade geometry, trying to extract knowledge from every failure. Even simple issues, like the engine's susceptibility to sand and debris ingestion, are noted meticulously. By the end of the first week, the engineers are exhausted but enlightened. They have witnessed the Jumo 004 roar, falter, and fail. Each test is a lesson in physics, metallurgy, and the harsh realities of high-speed aviation. For the USAAF, these engines are both a warning and a roadmap. They reveal what the Germans achieved, and what America must improve to surpass them. As the lights dim in the test cell, Reynolds looks at the jet engine, blackened and scorched from repeated runs. "One day," he says to no one in particular, "we'll make this work." And better. Outside, the Ohio night is calm, belying the cacophony of jet engines inside. But inside the hangar, the future of flight is being forged, one test at a time. The following days stretch into weeks. Wright Field hums with constant activity, the Me 262 and its Jumo 004 engines at the center of a whirlwind of experimentation. Engineers take turns running tests, disassembling engines, and meticulously recording every anomaly. Every failure is an opportunity for insight. Every scorch mark a lesson etched in metal. Captain Reynolds leans over a turbine blade, examining the heat discoloration that spreads like a web along the metal. "They were running this too hot," he mutters. "The metallurgy just couldn't take it." Around him, technicians nod, some scribbling frantically in notebooks, others staring in disbelief. The Germans had achieved what seemed impossible: jet-powered flight, but at a cost. Every engine that roared to life in these hangars would be dead within 20 to 30 operational hours, if pushed hard, far too short for sustained combat. The engineers conduct comparative studies, bringing in their own U.S. engines for side-by-side analysis. The contrast is stark. Piston engines, while slower, are reliable, serviceable, and forgiving. The Jumo 004, in contrast, is brilliant but temperamental. Bearings overheat, turbine blades warp, and compressors falter under stress. It is as if the engine itself is screaming in protest at the demands of flight. Lieutenant Banks, carefully logging oil consumption rates and blade deformations, speaks to Reynolds. "They did what they could with what they had, sir. Magnesium alloys, limited cooling, and the constant threat of supply shortages. It's amazing they got it to fly at all," Reynolds nods, recognizing both the genius and desperation that shaped German engineering in the final months of the war. One particularly tense afternoon, the engineers attempt a full-throttle run. The Jumo 004 howls as metal screams against metal. The floor plates vibrate violently. Instruments dance and flicker. For a fleeting moment, the engine achieves near-design performance. But then, a turbine blade fractures, sending the engine into a violent seizure. Sparks fly, alarms ring, and smoke fills the chamber. The technicians scramble to shut it down. Everyone exhales collectively, hearts pounding. "That's what we're up against," Reynolds says quietly. "Power without longevity. Speed without sustainability." The room is silent for a moment, the weight of understanding settling over the engineers. They are not just studying an engine, they are studying the limits imposed by wartime necessity, metal shortages, rushed design cycles, and operational compromises. Amid the technical challenges, there are moments of human reflection. The team wonders what it must have been like to fly the Me-262 in combat. Pilots faced engines that could fail at any moment, flights where the roar of speed could turn into the silence of mechanical catastrophe. The engineers imagined the German pilots pressing the throttle, trusting these fragile machines to perform as promised. It is a sobering thought, technological wonder shadowed by mortality. Yet the Jumo 004 also inspires. Ideas for improved alloys, better cooling systems, and higher performance designs are sketched on whiteboards and notepads. American jet programs, still nascent, will benefit directly from these insights. The engineers are acutely aware. They hold the blueprint of the future in their hands. Lessons forged in heat, stress, and smoke. By the end of May, patterns emerge. The engineers have documented the precise causes of failure: thermal fatigue, inadequate lubricants, metal shortages. They categorize failures by operational parameter, preparing reports that will inform post-war aviation development. Every crack, every warp, every scorched surface contributes to a deeper understanding of what makes a jet engine truly sustainable. Outside, the Ohio skies remain calm and deceptively ordinary. But inside the hangars of Wright Field, history is being made. The Jumo 004, though flawed, has revealed both the promise and perils of jet propulsion. The engineers are aware that the lessons learned here will echo far beyond the war, shaping aircraft that will dominate the skies in the decades to come. Captain Reynolds watches the engines one last time as the hangar quiets for the evening. "Genius is never simple," he muses. "Sometimes it comes wrapped in fragility. And sometimes that fragility teaches us more than perfection ever could." June 1945. The engineers at Wright Field have settled into a rhythm. Their work a blend of meticulous observation and relentless experimentation. Each engine run begins with the hiss of compressed air, the careful calibration of gauges, and the quiet murmur of technicians checking oil lines and fuel mixtures. Outside, the Ohio summer hums with cicadas, an indifferent soundtrack to the roar of jet engines inside the hangar. Captain Reynolds leans against a workbench, eyes fixed on a turbine blade under the glare of an overhead lamp. "See this discoloration? That's thermal creep." After a few hours, this metal softens and warps. That's why they couldn't fly these things continuously. His fingers trace the faint cracks along the edge. The room is silent except for the scratching of pens and the low hum of cooling fans. Lieutenant Banks records oil pressure readings, noting the sudden spikes that accompany high-speed tests. "The lubrication system, it just isn't enough," he observes. "The Germans didn't have the alloys we need to withstand these temperatures. They made do with scarcity." Indeed, wartime shortages had forced German engineers to substitute lower-grade metals, magnesium alloys that were light and fast-heating but prone to rapid degradation. The engineers conduct endurance tests, running the Jumo 004 at near full throttle for extended periods. The chamber shakes with each roar, sensors ping and flicker, and the floor plates vibrate like a drum. Within minutes, the turbine blades begin to warp, the casings glow faintly red, and small fragments of metal flake off. The engines are operating at the edge of possibility, a testament to ingenuity and the harsh limits of physics. "Imagine flying this over the front lines," Reynolds mutters, imagining the German pilots pressing the throttle with death at every turn. You're pushing a machine that could fail in moments. At 500 miles per hour, Around him, the engineers nod, silently acknowledging the bravery and desperation inherent in such flights. The team's analysis deepens. They examine the effects of repeated thermal cycling, the expansion and contraction that stresses the alloy, the fatigue that inevitably leads to fracture. Every observation is documented, every anomaly noted for later study. They map the precise failure points and simulate how improvements in metallurgy, lubrication, and cooling might extend operational life. Yet the fragility of the Jumo 004 offers insight as much as warning. American jet programs still experimental at this stage stand to gain immeasurably. The engineers discuss potential adaptations: heat-resistant alloys, more robust bearings, improved oil systems. Each failure teaches them how to build engines that will not just fly fast, but survive. There is a moment of reflection when Reynolds holds a spent turbine blade, blackened and twisted from heat stress. "It's beautiful," he says softly, "and doomed." Just like many of the pilots who flew it. His colleagues fall silent, imagining the skies over Germany where these engines roared, pushing machines and men to their limits. Despite the harsh lessons, excitement persists. The Jumo 004 embodies a quantum leap in propulsion, and every test run brings the engineers closer to harnessing that knowledge. They discuss how, with better materials and engineering, engines could exceed the Me-262's performance while remaining reliable. In their hands, failure becomes a guidepost, a roadmap for the future of aviation. By mid-June, the USAAF reports, compiled from Wright Field, are already shaping post-war designs. Insights gleaned from the Jumo 004 inform the development of the P-80 Shooting Star, the first American operational jet fighter. Engineers will carry these lessons into the Cold War, where jet engines will define air supremacy. As the sun sets over Dayton, Reynolds looks out the hangar windows at the calm Ohio horizon. Inside, the smell of scorched metal lingers, a reminder of both the potential and limitations of human innovation. "This is just the beginning," he murmurs. "What we learn here will echo in the skies for decades." July 1945. The hangars at Wright Field are alive with a different intensity now. The initial awe has settled into disciplined scrutiny. Engineers move with purpose, their eyes scanning for signs of fatigue and failure, their hands steady as they dismantle and inspect the Jumo 004 engines piece by piece. Each bolt, bearing, and turbine blade is a lesson in wartime compromise. Captain Reynolds convenes a meeting with his senior team. Spread before them are diagrams, fractured turbine blades, and detailed logbooks from weeks of testing. "Gentlemen," he begins, his voice low but firm, "we are dealing with brilliance constrained by scarcity. These engines were designed to get into the air quickly, to fight a desperate war, not to last." Lieutenant Banks points to a worn compressor fan. "The Germans had to rely on magnesium and other light alloys. It was fast, yes, but brittle. We can push it for a few hours, maybe 10, but beyond that, failure is inevitable." Reynolds nods. They are facing the stark truth that Me-262's revolutionary speed came at the cost of reliability. Pilots could not expect to fly more than a handful of sorties before risking engine failure. The engineers set up a simulated operational schedule, mimicking the sortie cycles a combat pilot might endure. Engines roar to life, are run for short bursts, then cooled, inspected, and restarted. Patterns of wear and stress emerge predictably. Cracks along turbine edges, warping of casings, degraded bearings. Each failure reinforces the lesson. They are witnessing technology at the limits of material science. Reynolds steps back, watching a turbine spin under full load. It's beautiful and terrifying. These pilots were betting their lives on this fragility. The team exchanges glances, imagining the skies over Germany in 1940-45, pilots throttling up, engines screaming, a moment of exhilaration before inevitable mechanical risk. Despite the limitations, the Jumo 004 engines provide an invaluable blueprint. Engineers debate modifications that might extend operational life: higher-grade alloys, redesigned lubrication channels, improved cooling ducts. Every observation informs plans for the future of American jet propulsion. One afternoon, Reynolds and Banks conduct a controlled failure test, intentionally pushing an engine beyond its limits. The turbine blades glow red-hot before twisting and breaking, fragments scattering inside the reinforced test cell. The sound is deafening, a scream of molten metal. The engineers step back, recording every detail. They know this knowledge is priceless. In quieter moments, the team reflects on the human dimension. They consider the German pilots who flew the Me-262 in combat. How many lived to return from a sortie? How many engines failed mid-flight? These questions underscore the peril of innovation under duress. Technology is not just about speed or power, it is about survivability, about balancing brilliance with endurance. By the end of July, the USAAF has a comprehensive understanding of the Me-262's strengths and weaknesses. The Jumo 004 engines, while revolutionary, are fragile. Their design limited by wartime materials shortages and the pressures of accelerated development. Yet in their shortcomings lies the roadmap for the next generation of jets. As evening falls over Wright Field, Reynolds walks among the engines, now cooled and disassembled. He pauses, fingers brushing the scorched metal. "History is written in steel and fire," he says softly. "And today, we're reading every page." August 1945. With the war in Europe over, Wright Field transitions from urgent testing to strategic application. The Jumo 004 engines have been run, dissected, and catalogued. The data is vast, technical, and invaluable. Engineers, now more experienced in jet propulsion than any of their predecessors, begin translating observations into designs for the United States' emerging jet program. Captain Reynolds gathers his team around a large drafting table. Spread across it are sketches of turbines, airflow schematics, and cross-sections of combustion chambers. "We know what works," he begins. "We know what fails. Now it's our job to take this knowledge and build engines that fly faster, longer, and safely." The men nod, their focus intense. Every detail from the Jumo 004 blade angles, compression ratios, thermal expansion effects is scrutinized for potential improvement. The team conducts simulations to test alternative materials, using metallurgical innovations that were unavailable to the Germans. Nickel alloys, stainless steel, and high-temperature coatings are considered to withstand the extreme heat that destroyed the Jumo 004 so rapidly. Engineers debate coolant flow designs, oil viscosity, and combustion efficiency. The air is thick with both the smell of lubricant and the tension of creative problem-solving. Reynolds observes a prototype turbine spun at half the maximum RPM. The metal remains stable, showing minimal warping under stress. "This is the difference between desperation and design," he says. The Germans had achieved speed with limited resources. The Americans now have the tools to combine speed with reliability. The lessons from failure are as critical as those from success. Engineers catalog every crack, every scorched surface, every warped blade from the Jumo 004, annotating how changes in metallurgy, cooling, or lubrication could prevent recurrence. These observations inform not only turbine design but maintenance procedures, operational limits, and pilot training for the new jets. In parallel, pilots are introduced to the concepts behind jet propulsion. Flight officers visit the hangars to observe engine tests and learn firsthand about thrust, fuel consumption, and temperature management. They are struck by the contrast to piston-driven aircraft. Jets respond differently, accelerate faster, and require a new understanding of aerodynamics. Engineers and pilots exchange insights, ensuring that knowledge will translate from the test cell to operational flight. By late August, plans for the P-80 Shooting Star, the United States' first operational jet fighter, are heavily influenced by the lessons learned from the Jumo 004. Turbine blade designs, alloy selection, and maintenance protocols reflect both the successes and failures of the German engines. What had been a fragile marvel now becomes a foundation for innovation, ensuring that American jets will not repeat the operational shortcomings of the Me-262. Reynolds walks past a row of engines lined up for final inspection. "We owe a lot to the Germans," he muses. "Not just for what they built, but for what they couldn't. Their mistakes are our lessons." His team works late into the evening, applying every insight, refining every component, driven by both curiosity and the urgency of post-war aviation development. The transformation is clear. Knowledge born from necessity, tested under fire and failure, becomes the blueprint for sustainable innovation. The Jumo 004 engines, once symbols of wartime genius constrained by shortage, now guide the United States toward a future where jet speed, reliability, and endurance coexist. September 1945, beyond the metal and machinery, the engineers at Wright Field begin to reflect on the human cost behind the technology they study. For every jet engine dissected and tested, there were German pilots who risked their lives, trusting fragile machines to survive combat. There were also Allied pilots who faced these jets in battle, often with little warning against speeds that exceeded their own aircraft's capabilities. Captain Reynolds organizes a briefing for his team, not about turbines or alloys, but about the broader context of their work. "We're not just engineers," he says. "We're historians of flight. Every crack, every failure, every test run tells a story about the men who flew these machines." The room falls silent. They are aware that behind every Jumo 004 is a narrative of bravery, desperation, and ingenuity. Lieutenant Banks recounts interviews with captured Luftwaffe pilots. Some spoke of exhilaration at the Me-262's speed, others of anxiety at the engine's unreliability. One young pilot had been killed mid-flight when his turbine seized unexpectedly. The stories resonate with the team, grounding technical study in the reality of wartime stakes. In the hangar, technicians occasionally pause, staring at a turbine blade or scorched engine casing. It's easy to get lost in numbers, one whispers, but these machines were alive to those who flew them. Reynolds nods, acknowledging that innovation cannot be separated from the human element. They are not only dissecting metal, they are dissecting the experiences of men who relied on that metal to survive. The engineers take deliberate steps to document both technical findings and pilot experiences. Notes include not just operational failures but observations on how pilots managed throttle, how they coped with engine limitations, and how missions were adapted to avoid catastrophic failure. These insights feed back into American jet design philosophy, emphasizing reliability alongside speed and pilot safety alongside performance. Reynolds reflects privately on the moral dimension of their work. "We can't forget the people," he writes in his log. "These engines were born of desperation, flown by courage, and tested by curiosity. Our task is to honor that by building something better, faster, stronger, and safer." The hangar hums with renewed purpose. Every test run, every adjustment, and every note is now framed not only by engineering goals, but by a deep awareness of human risk. The lessons of fragility, ingenuity, and bravery merge, shaping not just machines, but the culture of American jet aviation for the coming decades. October 1945, with months of testing behind them, the U.S. AAF engineers begin compiling comprehensive reports on the Me-262 and its Jumo 004 engines. These documents are exhaustive, detailing performance characteristics, failure points, material limitations, and operational recommendations. Every insight is carefully categorized, providing both technical guidance and strategic context for military planners and aircraft designers. The reports highlight a stark contrast between innovation and practicality. While the Me-262 demonstrated unprecedented speed, climb rate, and aerodynamic refinement, its engines could not withstand prolonged combat stress. Pilots could not rely on the aircraft for extended sorties without risking catastrophic engine failure. This knowledge becomes critical for the United States as it begins to consider its own jet programs. Reynolds presents findings to senior Air Force leadership. "The Germans were ahead in speed, yes," he explains, pointing to turbine diagrams and performance charts. "But their engines lacked durability. With better materials and maintenance protocols, we can achieve greater reliability without sacrificing performance." The room absorbs the gravity of the lessons. The Jumo 004 was a bridge to the future, not the final answer. The operational insights extend beyond design. Maintenance schedules, fuel quality, and engine handling are all scrutinized. The Americans learned that jet technology demands new logistical and training considerations. A fast aircraft is useless if ground crews cannot sustain it, or if pilots are unprepared for its nuances. This awareness shapes doctrines for jet operations that will influence the Air Force for years. Beyond the technical sphere, intelligence officers recognize the strategic implications. The Me-262, while dangerous, was not a war-winning weapon. Its limited operational lifespan, combined with production delays and fuel shortages, meant the Luftwaffe could not exploit its advantages fully. The United States absorbs these lessons, understanding that technological innovation must be paired with industrial capacity, supply chains, and pilot training to have real battlefield impact. Reynolds walks the hangar one final time, noting the engines lined up like silent witnesses. "We've learned what was missing," he says to Lieutenant Banks. "Materials, reliability, sustainment. Those gaps kept the Me-262 from changing the outcome of the war. But the knowledge we take from it, that can shape the next era of aviation." In the months following, the lessons from the Me-262 directly influenced the development of the P-8O Shooting Star and other early American jets. Engineers incorporate stronger alloys, improved lubrication, and better thermal management. Pilots train under new doctrines that account for high-speed jet handling. Ground crews adapt to new maintenance requirements. The entire ecosystem of jet warfare evolves from the crucible of Wright Field's tests. By the end of 1945, the captured Me-262s are retired to museums and storage, but their legacy endures. The Jumo 004 engines, once fragile marvels of desperate innovation, have transformed American aviation. Lessons learned from their limitations shape the design, deployment, and operational philosophy of an emerging jet age. By early 1946, the dust of war has settled, but the echoes of the Me-262 and its Jumo 004 engines continue to reverberate through American aviation. Wright Field stands as both laboratory and memorial, a place where engineers transformed captured technology into the foundation of the United States jet age. Captain Reynolds reflects on the months of testing. The roar of engines, the sparks from failed turbines, the smell of scorched metal, they all remain vivid in memory. We learned more from their mistakes than we ever could from success alone, he notes in his journal. The Jumo 004, despite its flaws, served as a crucial teacher, revealing the fine line between genius and fragility, between speed and reliability. The operational and strategic lessons gained extend far beyond engine performance. American jet programs benefit from a newfound understanding of metallurgy, lubrication, and thermal stress management. Pilots and ground crews are trained with the knowledge that reliability is as critical as speed. Doctrine, logistics, and aircraft design all evolve from the insights gleaned from the Me-262. The captured aircraft themselves find their way into museums, studied by historians and engineers alike. The Smithsonian Wright-Patterson Air Force Museum and others preserve examples, allowing future generations to witness the innovation that nearly changed the skies over Europe. These exhibits emphasize both the technical achievement and the human courage required to fly them. In the broader context of aviation history, the Me-262 and its engines leave a dual legacy. On one hand, they are symbols of revolutionary design, a glimpse of the jet age dawning before the war's end. On the other, they are a reminder that innovation alone cannot guarantee victory. Materials, maintenance, pilot skill, and operational support are equally decisive. The U.S. AAF engineers who studied the Jumo 004 carry these lessons into the Cold War. Their experience informs early American jet fighters and bombers, influencing design philosophy for decades. Every turbine blade, every scorched casing, every observation about thermal stress and rapid wear shapes aircraft that fly faster, longer, and more safely than their German predecessors. For the men at Wright Field, the work is both technical and profoundly human. They recognize the bravery of pilots on both sides of the conflict, the ingenuity of engineers under pressure, and the immense value of learning from failure. The captured engines are no longer just hardware. They are stories, history compressed into metal and flame. As the sun sets over Dayton, Reynolds walks past the display of retired Me-262 engines, now clean, catalogued, and silent. He pauses, reflecting on the journey from wartime discovery to post-war innovation. "We learned what was missing," he whispers. "And in that absence, we found the path forward." The Stormbird may have been a fleeting advantage in the skies over Europe, but its true legacy endures. The Jumo 004 engines taught the United States how to build the future of aviation, bridging the gap between desperation and design, fragility and durability, war and peace.